15, AP Mechanics. All right, let's go through this multiple choice test. All right, they give you three graphs. Notice they are position versus time. If we look at this first one, this is an object standing still. This is an object moving to the right at a constant velocity. This is an object moving to the right with increasing velocity. So this one has acceleration. These have zero accelerations. Okay, let's look at the first three questions. In which of the graphs is the magnitude of the momentum? Momentum is mv, and so which one has an increasing velocity? Number 3, and that one also then has an increasing momentum. Which of the following does the object have a constant, non-zero kinetic energy? All right, this guy right here, since it has a constant velocity, does have then a constant kinetic energy. This one would have a constant kinetic energy. It would just have a constant of 0. This one's velocity is changing, thus its kinetic energy is changing. In which of the graphs is the net force 0? Right? The net force is 0 when you have an acceleration of 0, which means when you have a constant velocity. So in the first two examples, there's no net force. Here we want static equilibrium. Static equilibrium means no net force, so the sum of all the forces have to equal 0. And this is 3 units up, and this is 3 units down. They cancel up and down. And this is also 2 units to the right, which then that would cancel 2 units to the left. So if you add those 3 vectors together, they all balance. And so that's why you get that one. All right, first thing you want to notice, we're looking at a constant speed. Constant speed must mean that the horizontal component of the pull force, usually we call that applied, must balance friction. So usually we say FA cosine theta minus F, meaning the force of friction, must equal 0, and then just add and then divide by cosine. All right, we're looking for the applied force. Okay, this is just impulse. So write down the impulse equation, right? We're looking for the average force during an acceleration, during a collision. And so the change in momentum, the impulse, is equal to F delta T. So the average force is just this delta P, which we know is just M delta V. In this case, delta V is just V because it went from rest to something. And so we really just divide by T to find the average force, right? Kind of classic derivation of impulse. The work done on the ball is just the increase of kinetic energy. The maximum height, okay, you can do this in 2 ways. Way 1 is above the blue line, and that is energy. So mgh, the potential energy gained by the original kinetic energy, and you have to be careful, we're only looking at the transfer of the vertical kinetic energy. The horizontal velocity stays the same, so that doesn't contribute to the height at all. So we're going to do mgh equals 1/2 mv squared, but v, we're only going to use v sine theta. And so if you do this equation, and again, the g here is g over 6 because we're on the moon. So instead of g, we're going to put in g over 6 and then solve that equation. If you also use the v squared equation, we would give the same thing. The maximum, or the velocity at max height here would be 0. The initial velocity would be v, v sine theta, and then a, of course, would be g over 6, and you'd get the same result. This next one asks about what happens if you we want to double the period of something. Well, doubling the period requires quadrupling the length, a whole double, triple type question. Again, write out the equation and then look at the relationship. T is related to the square root of L, so doubling T requires L to be quadrupled. This is the small angle approximation. Again, the period is independent of the angle as long as the angle is small. So oscillating pendulum 1 versus pendulum 2, they're going to have the exact same period despite having slightly different angles as long as theta 1 and theta 2 are both small. The lengths of them is the same. A newly discovered planet. Again, this is a double, triple thing. This is making the radius 5 times, but then squaring it is going to create a factor of 25 in the denominator, and then you're going to make it 3 times massive. So 3 times the mass, 5 times the radius is a 3/25 factor. All right, this one is a very interesting one. We usually do not talk about omega when we're talking about this elliptical orbits. Usually we say closer is faster, and we're talking about v, meaning velocity. Here we're talking about angular velocity, so we're talking about omega. So we're still going to conserve angular momentum, L1 equals L2, and we usually write down this next line right here. This line is usually mv1r1 equals mv2r2, and it's like, hey, you're 3 times farther away, then you're 3 times slower. Stuff like that, right? Farther away is slower, closer, faster. But we're not talking about v. They want omega. They tell you to you right there. They want angular speed. So instead of the definition of mv cross r for angular momentum, we're going to go ahead and use I omega. I for a point particle is just mr squared, and now we can do, well, what happens when we take half of r? Well, we must then be rotating 4 times faster. Again, I get it. We normally look at conservation of angular momentum with v's, but they wanted to look at omegas, and so we have to look at the different version of angular omega. We still conserve angular momentum because there's still no net torque as this object is rotating around in this elliptical orbit. All right, we got 2 objects. I believe we did this question in the MIT circular motion. We did a free response question. You can go back and look at that in that module if you'd want to. But if we're just looking at the inner ball, we know that the inner ball is moving in a circle. So we know F equals ma. The forces on the inner ball must be net inward. So T1 is pulling it in, T2 is pulling it out. Since it is moving in a circle, the inward force must be winning. So that's why I wrote T1 minus T2, and that equals mv squared over r. And instead of v squared over r, look at the answers. They just wrote omega squared r, which is fine. And again, in the r is specifically looking at the inner block, and that's at a radius of r1, which is why they did r1 there. This is just v squared over r. They're just asking for the acceleration of a block moving in a circle. Just knock it out. V squared over r, donezo. All right, elastic. They tell you it's elastic. That means that we're conserving energy, and of course we're conserving momentum because it's a collision. And so the only way you're going to conserve energy in this case is that these guys have the same mass, of course, that they end up basically just switching who's traveling what speed. So when x collides with y, x has to go back left with 4, y has to go to the right with 2. So momentum will be conserved because you're still going to have 4 to the left and 2 to the right afterwards, but you'll also have the same amount of energy afterwards and before. So that's the only way it's going to work. Right? They basically just flip-flop exactly what they were doing. Okay, here's a different collision. This is completely inelastic, and that means the object's stuck together. And so this is the idea of momentum must be a vector. So again, they're not asking for velocity, they're asking for momentum. The momentum originally, that guy is 3 mv to the right, and this is 4 mv up. And when you add them together, the magnitude is, you cannot just straight up add them because one is right and one is up. You have to add them like vectors. And so it's the hypotenuse of that vector, which ends up being 5, right? It's a 3, 4, 5 triangle. Don't just add them and try to get 7. You'd only add them if they both were to the right or they both were up. One right and one up, add them like vectors. Right, this one, on the key, all of this blue is correct, but unnecessary. Okay, I didn't actually read the question. I just started analyzing them. This blue would solve for the coefficient of friction. Well, they didn't actually ask for that. They only asked for the force of friction. It looks like this is a little bit like cut off, but I don't want to risk messing this up. But this over here says mg sine theta minus f equals ma. This is right over here. This is just me saying, what are the forces acting on this thing? Mg sine theta is down the ramp, force of friction is up the ramp, and that equals ma. And all I did was just plug in for what everything is told, and then you get the force of friction must be 4. Again, this is correct. It's just overdoing it a little bit. You don't actually need the coefficient of friction. You just wanted this entire term. So instead of mu mg cosine theta, just put ff and then solve. 18, all right, well, we're pulling this top box, but they're staying connected. So view those boxes as just one massive box of 6. And that's where I get this line right here. You're pulling a 3, you're pulling a box that's a 6, and thus you accelerate at a half. And then you go to the bottom box. You're like, all right, what's actually happening now? Okay, so if we look at the bottom, there's no friction between the bottom box and the floor. So get rid of that. So then the only force making the 4 kilogram box move is the friction between these two boxes. So the force of friction, which is mu mg, and that mass is the 2 kilogram. The friction is caused by the 2 kilogram rubbing on the 4 kilogram, but that friction is causing then the 4 kilogram box to move to the right with an acceleration of a half. So when you plug into this equation, just notice that the m here in friction is the 2 kilogram, but the m here is the 4 kilogram. The 2 kilogram one is causing the friction, causing the 4 kilogram one to accelerate. So you gotta be really careful with these m's are not the same. These questions are, I don't know, very wordy, but they're not difficult, and they're just, I don't know, it feels like they're just trying to trick you. The magnitude of the acceleration of the center mass. Well, all 3 of them are just in free fall. So they're all falling at g. So if you combine them, well, then, yeah, they're all falling at g. So of course, then the center mass is also then accelerating at g. However, the velocity of the center mass, again, is like the average velocity of this system. Well, you have to take each mass and multiply it by the velocity it's going, divided by the total mass. This formula is very similar to the center mass formula. It's just the center of velocity formula. So we have an m moving at v, we have 2m moving at nothing, and a 3m moving down at v. And so add that combination together and divide by 6m, and then you get the average velocity of the system. This is just a vacuum pump, right? So this is a vacuum pump means there's no more air resistance. No air resistance, the coin and the feather do the exact same thing because they're falling with the exact same acceleration, exactly g. This is a velocity versus time graph. The speed is decreasing and then increasing, where the velocity is decreasing the whole time. But the speed decreases to 0, and then it does actually move to the left, right? Because we have a negative velocity down here, which means we are moving in the negative x direction. Okay, this is kind of comparing, and this is something we have discussed, hanging something versus dropping something, and we have decided that when you hang something, it's in equilibrium, which means that kx equals mg, and you get where it would hang would be mg over k. If you drop it, it's an energy thing. You're like, well, mgh would then go to elastic energy of 1/2 kx squared, and you figure out the height it would fall would be 2mg over k. And you can see that the height it would fall is double that distance. And again, if it would go down 0.1, well, then it's actually going to fall down all the way to 0.2 and then reverse direction and bounce up and down, boom, 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 up and down from that value. That would be that center point, and then this would be the total distance it would fall. All right, this kind of 2 things here. The first part, it does tell you that this is hanging. So remember, that's the hanging part, and that hanging part gives you information. It gives you enough information to figure out that the mass is 0.5 kilograms. Well, once you know the mass is 0.5 kilograms, then you can figure out the work done by the block moving along that path, because you know the work done is just the change in potential energy. So you got to use this piece here to find the mass, and then once you know the mass, you can actually find the work done. And again, we only care about the vertical distance, right? This 3 meter vertically is all we care about. This is completely irrelevant. Okay, so they give you some equation for this rotation amount. This is a torsion pendulum. If you remember a torsion pendulum, I mentioned it. It appeared one time on a free response question, which we did in class. And then this is another example of it appearing on a multiple choice question. The torsion pendulum is like the kid on a swing, and we're twisting it. they're giving you this equation of twist. Now you have to know that that number right there, that little 2 guy, that's omega. And then if you look at the torsion equation, torque equals I alpha, the torque is negative K theta, right? The torque is opposite proportional to the amount you've twisted the kid on the swing. So if you look at this, we know that in a torsion equation, omega squared is K over I. And so then you come up here and you're like, oh, well, if omega squared is K over I, and omega is 2 based on the equation, and I is 10, then I can figure out what K must be. Again, the K must be 40. You got to think that all the way through, but you did have to remember that the torsion pendulum, that the torque of the torsion pendulum was negative K theta. Remember, the torque is proportional to the amount you twist, theta, and then the material, K, and then, of course, the negative sign is because it's a restoring torque. If you twist it one way, it's going to want to twist back the other way. Okay, so this is like, instead of the ice skater changing her moment of inertia and her spinning faster, this is just a diver flipping off of a board, but it's doing the exact same thing. The diver changes their rotational speed by changing their rotational inertia. So they go into a really tight tuck and they're going to spin a little faster. And then if they release their tuck, they're going to stop spinning and then, dive. This one is a momentum question. So you launch this thing and it explodes, all right? A spring releases 2 toys split into 2 parts. That's an explosion. Think momentum. The smaller mass is going to have a bigger velocity that way. The bigger mass is going to have a smaller velocity that way, right? We know that they're going to go in those directions. But that one and that one have the same momentum, but bigger mass, smaller velocity, smaller mass, bigger velocity. Bigger velocity is going to go farther on the ground than this one. Okay, so what's true about the bigger mass? It's going to strike the ground closer. So that one. Right, this is center mass, and this is just in 2 dimensions. So we got x hat and we have y hat. So there's a mass there, and a mass there, and a mass there. And we just take those 3 masses and we plug them into the center mass equation. This is me taking each mass in its x position, and this is each mass in its y position. And I'm finding then the x and y position of the 3 combined masses. This is classic pendulum, the speed of the ball as it swings through. This is just conservation of energy. This is mgh goes to 1/2 mv squared. So we got that. As it swings back and forth, mechanical energy is going to be conserved because there's no drag forces. So energy just goes back and forth between potential and kinetic. But momentum and angular momentum, no, those things increase and decrease because, well, linear momentum increases and decreases because there's forces, gravity, and angular momentum, there's torques. Gravity causes a torque. So these things are not going to be conserved in external force and external torque situations. You see this and you immediately, they don't tell you necessarily that it's a spring, but you instantly start thinking that that guy is a spring. So if it's a spring, it's got a 1/2 kx squared, and then the force is going to be some negative kx. And again, I didn't put a k in there or a half. It doesn't matter. It doesn't have to be even a spring, but it sure looks like the potential energy is some x squared, and then the force is going to be some negative 2x. Remember, the force is the negative derivative of potential. It has to be. If you increase your potential, it's because the force is in the opposite direction. You are increasing your potential energy as you fight against gravity up. Oh yeah, because gravity is pulling you down. You increase your potential energy stretching a spring. Well, yeah, because the force of the spring is in the opposite direction. Okay, now they've asked on the last test, I think the 2014 test, they wanted the potential energy equal to the kinetic energy, and we said that was A over radical 2. Well, this one's the easier version because we want the kinetic energy to be 3 times the potential energy, which just means we want to cut that guy into half. Think about it. 1/2 kx squared. If we make x over 2, we're going to make the potential energy 1/4 of the total, which would make the kinetic energy 3/4 of the total, which would make the kinetic energy 3 times the potential. Again, cutting x into half cuts the potential into a quarter, which would leave 3/4 of the energy to kinetic. 3/4 is 3 times 1/4. And so just cut 4 centimeters into half and get 2 centimeters. That's a whole double, triple question. So is this next one. This is Kepler's third law, second law. And it says that the period squared is proportional to r cubed. And again, the only numbers that really work out well here are 4 and 8. 8 squared is 4 cubed. Definitely something you want to remember. So a 4 here leads to an 8 here. This one you're just going to look for when the force is equal to 0. We know that maximum velocity occurs at equilibrium. Equilibrium is when the force is 0. So this is very similar to like a calculus question where we don't have to take a derivative, but we're going to factor this, and we're going to look at the time at which the force is 0, and we're going to do a sign chart. And this is me saying that the force is positive from 0 to 2, which means if the force is positive from 0 to 2, we are accelerating from 0 to 2, thus we've reached maximum velocity at 2. And the last one is just an old school vector equilibrium question, right? Draw a free body diagram, which I did here. I didn't label this, but we are looking at the ups and the downs, and the up forces, remember, that's a weird angle. That angle is drawn with respect to the vertical, so t cosine theta would give you that amount. T cosine theta would give you that amount. So then 2 t cosine theta minus mg down would have to equal 0, and then you just solve. And that is 2015 mechanics.